now. Cool. So we are talking about heat. Now, we've talked about this a little bit, even though maybe you're not completely aware of it. We have talked about stuff and temperature. So there's an important distinction there between, I pushed that over too far, that's stupid. So, but we're talking about the difference between heat and temperature. And can somebody give me a quick definition of temperature, what that means? If something is, if like the air is, today it's getting warmer, so outside it might be 25 Celsius. What is true of the air at 25 Celsius compared to if the air is 10 Celsius? Tell me something about the air. And I could call on somebody, that might be better. So let's do that. Or just somebody speak and throw themselves in front of the bus so that nobody gets called on.
Maybe, so the warmer it is, the more heat there is, and the colder it is, the less heat?
Yeah, that's not right. That's cool. I like it. But that's the common misconception because it's the kind of the general use of the word heat. And that's why I kind of put it in quotation marks, because when we talk about heat in everyday language, we're like, wow, what a heat today. It's like, oh man, it's really hot. But what we're really referring to there in a physics sense is the temperature, that the temperature is high. Okay, so that's an important distinction. So that's not quite correct. I'm trying to stay away from heat right now. Don't use the word heat in this conversation. Earlier on in the class, I hope you guys remember, we talked about what temperature means, and maybe somebody remembers what temperature means.
Is it just how warm something is, or how?
It's a synonym for that. So high temperature means something is warm, but warm just means it has a high temperature. So you're kind of going in a circle there. Hi, Savoy. Did you say something else? I just speaking over there a little bit there. Okay. Why don't I just tell you what it means? Okay. So we're going to consider this a review. Okay. So I think you guys have not remembered. That's okay. So let's go with the word temperature for a second. And I'll give you guys a hint why.
Noel's right now.
Hilda?
Sorry.
What? Oh, sorry, Mila?
Noel's coming in right now.
Noel's coming in right now. Good. Okay. Cool. Cool. So I'll give you a hint here. When we talked about temperature, we introduced the concept of absolute zero. And why did we introduce that concept? What's true of absolute zero that kind of grounds the concept of temperature? Maybe that's a good kind of boost for you guys to remember how temperature works. Somebody want to jump in? I'll ask Tees. Let's see if Tees knows. What does absolute zero mean? That's like 0 Kelvin, right? What does that concept mean? You forgot? That's okay. Good. I'm so glad we're doing this review. Let's try to call on somebody else. How about Charlotte?
I'm also not quite sure. Actually.
Okay, that's cool. We'll just keep throwing people under the bus. How about Kian? Do you remember what absolute zero means?
No, not quite.
Not quite. Okay. Does anybody know? Or should I just tell you?
I think I might have an idea.
Good.
It's the absolute zero heat, like there's no heat at all.
Okay, there's no temperature, but they were kind of defining it in circular. So it's the lowest temperature possible, and no temperature is possible that's lower. Why?
So because the molecules are already standing still.
Perfect. That's correct, Savoy. Exactly. So we have.
I'm Ari.
I'm sorry, Ari. Sorry. So we have a temperature at zero temperature, like Ari just described. We have all motion ceasing. Okay. So at 0 Kelvin, the particles are not moving at all. Okay. And that should give us a hint to what temperature means. If we have 0 temperature, the particles are not moving at all. If we have 100 Kelvin, the particles are moving a little bit. And if the temperature is 200 Kelvin, the particles are moving faster. Okay, so temperature is a measure of how fast particles are moving. Okay, so temperature measures how fast particles are moving. So back to my original question, if I ask that question I asked earlier about the temperature outside, today it might reach 25 Celsius, and maybe in March we had 10 Celsius. So what could you tell me about the air today at 25 Celsius compared to a day when the air has a temperature of 10 Celsius?
Oh, can I say something?
Sure, Liz.
So, from what you just told us, I guess that on a day that it's 25 Celsius, the particles are moving a lot faster than on a day that it would just only be 10 Celsius.
There's an awesome goodness in there, and there's an awesome thing that hints to me that we need to review something else. So Liz, you're correct. It is moving faster. Why did you say it's a lot faster?
Well, because this is Celsius, not Kelvin.
Aha. So you said because 25 is so much bigger than 10, correct? That's
It's
why
not.
you,
Yeah.
right?
Well, yeah,
Okay,
proceed.
now I think you're fixing it, and I think that's really awesome. So tell me about, so you said initially the particles are moving a lot faster, and that's actually not true. They're moving just a little bit faster, but you felt that made sense based on the fact that the temperature is 25 Celsius versus 10 Celsius. But what temperature, and I'll let you fix it here, Liz, what temperature scale should we use to get an idea of how fast the particles are moving?
Kelvin?
Good. Exactly. So we need to use the Kelvin scale to get a relative idea. Hi, Noel. Good to see you. Can you turn your camera off too?
Okay.
Thank you. So it's a measure of how fast you're moving the particles if you are using the Kelvin scale. So just a reminder how to do that. Okay. So we do Kelvin. We take, and this is in Germany, our big scale. So this is why we should definitely remember how to do this. You take the Celsius temperature and you add 273 to it. So our specific example was 10 degrees, right? That's a spring day, right? Oh, 10 degrees Celsius, right? Like that. So 10 degrees Celsius is how many Kelvin? Somebody jump in here. Just shout it out. Anybody. Either you're shy or you're really confused at this point.
283 for like
But 283 is right. 283 Kelvin is right. So this temperature would be 283 Kelvin, right? All right. And now we said maybe today it's 25 degrees Celsius. And how many Kelvin is 25 degrees Celsius?
298.
298. And you see right away. Now, we don't need to get exactly into how much bigger 298 is than 283, but it's really not a substantial difference, right? Makes sense? Yeah, that makes sense.
Yeah.
That this number is very similar to this number. So even though we can feel the difference when we go outside between 25 Celsius and 10 Celsius, in terms of the absolute difference in speed of the particles, it's not a huge difference.
Mann, das ist ein Meeting, du hast du auch. Das ist dann cool. Geh doch jetzt mal weg.
Noel, yeah. Turn your microphone off, please, Noel. Okay, good. Oh, here's a hint too, if you guys, but I'm sure you guys know this. You can turn, if you're on a laptop or a desktop, you can turn your microphone off and then you can use your space button when you want to speak rather than having to go back and forth, and you can just push the space button. It works on Zoom at least. That's a pretty snifty little technique. Okay, good. So I think we have a better idea of what temperature means. Temperature is a measure of how fast the particles are moving. Okay? Does that make
Mann,
sense?
jetzt musste ich die Scheiße schließen, weil ich nicht immer doppelt höre. Warum? Mann, ich habe die Kacke 5-mal geöffnet, weil die Scheiße sich automatisch öffnet.
Okay.
Mann, geh doch jetzt mal, ich kann es doch selber machen.
Hey, Noel, we can hear you, buddy. So I think you'd probably want to turn your,
Mann, jetzt geh doch mal.
microphone off. Okay.
Ja, wenn mich nicht hört.
Du kommst auch mit dem runter. Wenn ich meine Dings habe.
Okay. Good. I turned Noel's microphone off. Okay, good. All right, cool. And there we go. So I hope that makes more sense in terms of what temperature means. And now we can get to the concept of heat. And I'm going to give you guys an apology that heat is a strange concept because it's not actually a property of stuff at all. Temperature is a property of stuff. Oh shit, it's more complicated than that. Okay. All right, we'll get to it. Okay, so temperature I think we understand. Let's just kind of not talk about it again, but make sure that we are cool. Can somebody tell me that they feel comfortable, that they understand what the concept of temperature means in terms of how two materials are different when they have different temperatures? Is that correct as a group? Are we okay with that now that we've reviewed it?
Yeah, I think so.
Okay, good, great, perfect. So I'll take a quick picture of this and then we'll start talking about heat. And then later on I can post this to our classroom site. So I got a picture now. Good, we got temperature defined. So at this point, I'm going to give you a little analogy, okay? So we can think of the particles in the air, yes? And I want to think about those particles as a bigger particle. So let's imagine, oh, this is fun, okay? Let's try this. I'm not sure this is a perfect analogy, but it's good enough. Okay, so let's say we have a rolling office chair. Yes, that's a fun toy. Do you guys agree? So you've got a rolling office chair. And you have a friend. Imagine you have a friend. That would be cool. I'd love to have a friend too. So here's your friend on an office chair, okay? And right now, your friend's not moving, okay? So if your friend who's sitting in the office chair is not moving, the temperature, I mean, of course, this is heat. Your friend's representing a particle, right? So if this was a situation like that, what temperature would this be in Kelvin? I mean, it's a metaphor, an analogy, but okay. So your friend not moving, what temperature is that?
0.
0, exactly. So we're going to say this is like 0 Kelvin, right? And now, as you've all done before, I'm assuming, you're like, this is going to be fun because what we're going to do is I'm going to push you, and that'll be fun. You look a lot bigger than your friend, but let's just run with it, okay? So you're going to push your friend, right? And make your friend go faster, right? And as you push your friend a little further down the way, okay, here my drawing skills are tested. Cheep, cheep, cheep. Here your friend's going a little faster. You too are going a little faster. You're pushing it, right? Okay, and you look like you have a bent neck that looks unhealthy, plus your arms coming out of your stomach, but whatevs, okay? So you're moving faster here, okay? Let's say this would be 100 Kelvin, just for kicks. And then over here, you're going even faster as you keep pushing your friend along the surface. Oopsie, sorry, your arm's over there. And here's your friend. Now you're floating, that's not good, but you get the idea here. Whoop. I'm using the international distinction of how to indicate speed by using bigger lines to say you're going faster. T equals 200K. Does that make sense so far? So just that your friend going faster is the higher temperature. Everybody cool with that?
Mhm.
Yeah.
Good. Okay. Now, how does heat factor into this? So really, heat. Oh, hey, colors. Colors are pedagogically so intelligent. So because heat is red, we'll use red for that. So what here is the heating process? Well, the heating process is the process that we're undergoing here, that you're pushing this person, this friend, this pretend friend, if you imagine you had a friend. So as you're pushing the person, you're heating, and that is heat, the changing of an object's status by inserting energy into the situation. Okay, so heating or heat refers to this process here. The person that's pushing this thing is heating the material. Okay, so this is kind of the analogy. And then of course, if we think about this in terms of like actual heat or heating occurring to change a temperature, you'd be looking at maybe a pot of water on a stove. So you've got your water. On a stove, and then you literally have, imagine you have a gas fireplace, gas stove, and this thing is here's heating occurring. So then of course here the temperature would go from this temperature then up. So here maybe first temperature is 20 Celsius, right? Then you're cooking spaghetti. So later on, we'll just draw one. You'll have over here your pot, and you still have your, is that on my own screen? This red's hard to see. This one instead. I hope this one writes better. This one does write better. So we have over here more temperature change. There we go. Okay. So there's more heating. So it was 20 degrees. And later on, when you're trying to get it to 100, and that spaghetti pot takes forever, as we all know. Now we might be at 50 degrees Celsius. Okay. So this part here, that heat is changing the energy of the water the way that you, when you're pushing your friend, are changing the temperature and therefore the energy of your friend. And your friend looks a lot smaller here for some reason, but whatever. Okay, so that's the idea of heat. Heat is the idea of changing the energy of a material by putting energy in, or you could also go the other way and you have basically removing of heat, which would be kind of like a cooling process. Okay, I think it's a little bit confusing, but I hope maybe the colors help. Temperature is a measure of how fast it's moving, and heat, the concept of heat, is related to putting energy into or out of the system in order to make the particles change their status. Wow, that's very generic, and I'm not sure that's really super duper easy to understand. So I'm just going to check back with you how you feel about that.
Can you repeat the definition of heat? Because
Sure.
I have like
Let's write that down, and let's see. So let's write both of those down. So temperature and here I'm going to so Temperature is a measure of the energy and therefore speed of particles. And we'll add to that at 0 Kelvin, particles have no energy and therefore no speed. Okay, so I just want to kind of make sure we consolidate our understanding of that. I think that's a pretty good definition. I feel okay about that. Are you guys okay with that concept as well?
See.
See? Okay. Gracias. Okay, good. So that's temperature. Good. And then in contrasting that with heat or heating is really maybe, I really don't like this word, but sometimes we use words in physics just because they've been used for a long time. So sorry about that. So the idea here is that heating, I'm going to try to write down here. Can I push this thing up? I'm going to just have to kneel next to this thing. That's awkward. Okay. So, all right. Okay. Heating. So that would be transfer of energy into or out of substance which can change its temperature. I feel actually pretty good about that now. I mean, I already understood it before, so there we go. Okay, can you guys see that? Is that on the screen? See where we are here. That's kind of hardish to read. Let's see if I can actually lift this up. Oh, wrong direction. Stupid. Oh, well, hello. Where have you been all my life? There we go. So, I think we're going to get a better angle now. Pull this a little closer. There we go. So, heating, transfer of energy into or out of a substance which can change its temperature. Contrast that with temperature. Temperature is a measure of the energy and therefore speed. We're too close here. Sorry about that. I was feeling like that would be really helpful, but we're too close. Move this chair back. I have a very high-tech studio here, if you can't tell. Okay, so laptop on a chair is not really. I need a camera team here. Kidding. That would be cool. All right. Chair could fall off. That would be bad. Okay, a measure of the energy and therefore speed. There we go. Now we got it. So temperature is a measure of the energy and therefore speed of particles. At 0 Kelvin, particles have no energy, no speed, zero speed. Okay. Heating, transfer of energy into or out of a substance. Let's put an A there. That would be helpful, I think. Of a substance to substance which can change its temperature. Okay. All right, cool. And I think is that clearer now that we've spelt it out?
Yeah.
Okay, good, cool. So, and I think the analogy is really, I think, is helpful. So you think about this process, you're pushing this person and they're changing their speed is kind of like the flame on your cooker pushing the particles to make them go faster. Okay, that's kind of a very good analogy. And we're almost done, okay? But I want to have one last conclusion that we get to. And this is very intuitive. So if you think back to your friend, just imagine again you had a friend, and now imagine you had two friends. I mean, that's crazy, right? I mean, well, how awesome would that life be, right? So you've got two friends, okay? And one's this kid, okay? And you have another friend who's a little bigger. Okay, so a bigger person. So you have a bigger person and you repeat this process with a bigger person. And you push them, okay? And in that process of pushing them, well, you're as strong as you are. What will be true of your friend, bigger friend's speed at the end of the process? Compared to your smaller friend, if you do the same game with them. So you push your smaller friend 10 meters, and then you push your bigger friend 10 meters. What's going to be true?
Probably your bigger friend won't be as fast.
Your bigger friend will not be able to move as fast. That's correct. So that's great, and that's exactly also what happens with substances. So some substances will get fast more easily, and other substances will get fast not as easily, because some substances are like small people and some substances are like big people. And you guys know, for example, that in this analogy, the pot heats up like that, but the water is really slow to heat up, okay? So the water is kind of like your big friend, and the metal is like your smaller friend. So the heat coming from the flame gets the temperature of the metal to go up very fast, very easily, because metal is easy to heat, kind of like a small friend is easier to push. And then the water is very hard to heat up because water is more difficult. Kind of like you have me sitting on that chair and you're like, crap, Westman's heavy. So you get the idea. Okay? Makes sense?
Yes.
Good.
Yep.
We are done for today. We didn't get as far as we wanted, but that's totally fine because I think we did some important stuff, and it's such an important distinction between heat and temperature. So I'm actually quite happy where we are. We will meet next week, and I'm planning on probably the same time, but I have to look at the schedule because things are changing constantly. One thing before we log off, please return your books. If your homeroom teacher has talked to you about that, great. If not, either way, we need your books back at some point. So just have that in mind. I'm sure you're thinking of that anyway, but we'll have to collect your books back, and just be aware that that should be happening sometime soon. Cool. Okay. Hope you have a great day, and I'll talk to you guys soon. I'm going to post this, and I'm ending the recording first of all. Now recording.